When you wire up a massive industrial furnace or a heavy-duty packaging line, you're dealing with raw power. And the only thing standing between a controlled process and a thermal failure is a small plastic box, the temperature controller. A lot of people find these menus intimidating. But whether you have a Selec PID 500, a Hanyang AX, or a Hanyang VX series, they all operate using the same underlying logic. Today, we are going to configure the sensor, route the output, set the safety alarms, and run an automated tuning sequence so your system locks onto its target with precision. Before we press a single button, you need to have your unit wired up, and you must know exactly what type of sensor and relay you installed. Once you grasp the universal principles behind these menus, you remove the guesswork, turning a complex electrical chore into a repeatable, universally applicable skill. Step 1 is establishing communication. We have to tell the controller exactly what kind of hardware is listening to the temperature. In the Select manual, the Universal Input Parameter, INPT, tells the brain to look for a specific thermocouple, like J, K, or T. The default column shows it assumes a J type. If you wired a K type without changing this, your controller processes incorrect data. Now that the controller hears the temperature, we route its signal to the heating equipment by finding the output parameter, label it out O. It's a common misconception that the controller directly powers the massive heater elements. Its internal relays simply aren't designed for that massive electrical load. Instead, the controller sends a small, low-voltage control signal out of its terminals. That signal goes to an intermediate device, like a solid-state relay, or SSR, which then bridges the high-voltage current to the actual heater. Matching physical hardware to the digital input and output parameters is the foundation of your setup. This prevents system failures before turning the heat on. With communication established, we must build a safety net. If a component fails and the heater runs out of control, we need a hard kill switch. In almost every controller menu, you'll find these safety alarms labeled as AL1 and AL2. Navigate to your first alarm setting now. The configuration sheet illustrates this perfectly. You calculate a maximum safe limit, usually 15 degrees above your target, and set that as your high alarm. If heat crosses into these hatched alarm state areas, the controller intentionally breaks the heater circuit. Setting the AL1 limit is the final safety check, ensuring that a simple glitch does not escalate into catastrophic hardware damage. Now we give the system its brains. The controller fires the heater using one of two methods: basic on-off control or PID control. On-off control acts like a light switch. But because industrial heaters have residual thermal momentum, the temperature will wave wildly, overshooting the target even after the power is cut. If you are using an on-off setup, you must program a parameter called hysteresis, sometimes labeled as deadband or HYS. Hysteresis forces the controller to wait for a specific temperature drop before clicking the heater back on, preventing rapid mechanical switching that can destroy relays. The professional method is PID control. As the temperature approaches the target, a PID system predicts the momentum and pulses the power, allowing the temperature curve to lock onto the target line without wavering. You do not need to calculate the proportional, integral, and derivative variables manually to make this work. Instead, we use AutoTune. The manual defines this as the controller automatically measuring process characteristics. By pulsing the heater and observing this time proportioning graph, the algorithm measures the proportional band and overshoot to calculate the P, I, and D constants for you. To start this, you trigger the AutoTune command, usually by holding down two buttons. On this faceplate, look for the T or A light to start flashing. This tuning process can take several minutes. You must not interrupt it or power down the machine while that light is flashing. Offloading thermal math to the AutoTune algorithm ensures the controller sets its own PID constants, providing stable temperature control without manual trial and error. You'll know the process is complete when the AutoTune LED indicator stops flashing. Look at your main display. Your process value, the current temperature, should now be locked onto your set value. The buttons and menus vary by brand, but the core logic of input, output, alarms, and AutoTune remains consistent across the industrial controllers we have looked at today. Correctly programming these parameters prevents the temperature overshoots and safety shutdowns that occur with a default factory setup. Hit subscribe for more practical automation guides. Drop a comment if you have questions, and I'll see you in the next video.